Hey, what's up, guys? Welcome to my algebra geometry video. So this video, I want to talk about the reduce and the reduced skin and the irreducible skin and the integral skin and their connection. So this is a copy from my previous video. If you haven't seen this, you can check out. So a skin is irreducible uh if X is irreducible topological space. Okay, and okay. And if skin is reduced, means that every open set is a reduced ring. So reduced ring means there's an nilpotent. And in the future, that I will provide another video, maybe very short proof to prove that this is equivalent to each stock is a reduced ring. You can check out by yourself. Okay, and if the skin is integral, means that each open set, the Schiffer ring is a integral domain. Okay, so in Harshon, proposition 3.1, or in the Vacal, I think there's an exercise just to tell you that skin X OX is integral if only if the skin is reduced and irreducible. Okay, so in this video, I'm gonna to prove this. So this is our goal. Okay, and you can check out the Harshon, but the Harshon proof not requires some exercise. Okay, so it's like in algebra geometry, it's very difficult because those textbook, the author is a little bit lazy, right? They don't need to write. They don't have to write everything. So this is why I can make a YouTube video. Okay, so our starting point is that we want to show that if XOS is integral skin, if only if XOX is reduced and irreducible. Okay, so it's one of Harshon's proof. Okay, so reduce means that each guy is a reduced ring, right? So and irreducible is basically means that it's connected. Okay, so one direction should be very simple, right? Because if S in imagine that integral should be much more powerful, right? So let's say X OX is integral. This means that for all open set U open in X, that OX U is integral domain. Is integral domain. So obviously that then OXU is reduced because integral domain means that if in integral domain that you have fn equals 0, then must f equals 0, right? So it's reduced. Okay, so and so the rest is to prove that to show that XOX is irreducible. Okay, and hopefully this is simple for you, right? Because if X, oh, why always jump by itself? Let me just check out. Oh, where come from? Oh, sorry. Okay, so now we are going to prove that it's irreducible. So suppose X can be written as the two non-empty disjoint open set U1, U2. So let's say this is non-empty. And disjoint union. Okay, disjoint union. Okay, then by shift property, right? By shift property, you know that in order to specify the global section or the function on X, you need to specify both, right? U1 and U2. And conversely, if you specify U1 and U2, then we prove that you specify this. Also, shift property tell you that the shift ring is basically the OX on, sorry, it's basically OX on U1 and the products OX on U2. And then this is the product of ring. Okay. So let me just quickly recall that if somebody give you two ring, which is both non-empty, called R cross S, and so each element is RS, right? So R belongs to R, small s belongs to S. So what's the addition? So addition is very simple, just R1 S1 plus R2 S2 is basically R1 plus R2 S1 plus S2. And what's multiplication? So R1 S1 times R2 S2 divided by R1 R2 S1 S2. Okay. And so what is the identity, the identity element for addition is 0, 0, right? So 0, 0 is 0, right? Okay, so this tell you that the immediate tell you that R cross S is not integral domain. Okay, so proof is very simple, just one line, right? Because you can take 1 R 0 S times 0, 1 S. Okay, so these two are both non-zero. Okay, because in the non-empty ring that the 1 cannot equal to 0. Okay, so it's get 0, 0. Okay, so violate, so R cross S is non-integral domain. So this tell you that OXU, if X is reducible, or sorry, if X is reducible, then your OXU cannot be integral, right? But this violates your OXX, your global section OXX cannot be integral. But by definition, that integral domain means that for every open set you put in, they must be integral. So this contradiction. Okay, so we finish these directions. Okay, so okay, so the next part is that we are gonna to show the converse. So converse. So we need to assume that the X is reducible and then reduced, and we're gonna show the X is integral. Okay. Okay, so this proof it's a little bit tricky because in algebraic geometry, this kind of proof is usually need to glue the local property into the global one, right? So this type of proof use some technique, like yeah, you need some technique to help you. Okay. Okay. So let me just make the technique. So the idea is that I think in at least for my understanding, usually in this type of scheme proof, general scheme proof, right? You are not gonna you cannot easy to prove this, right? So the only way you can do is that you check, right? Or you check the property, or you check the statement. It's true on a fine subset, and then you try to use the gluing property so local to global, right? You try to use global property to prove something. So basically, the key statement or the key technology is that, or the technique is that you always focus on the affine subset. And if statement is on affine subset true, then you try to use the gluing property or the sheaf property to prove something that that you need to do. Okay, so this is the general strategy. Okay, so in order to do this, we need a very simple lemma. So let me just write down lemma. So this lemma tell you that, right, let's say X OX is a skin, and then you take F to be X OX. And okay, so we can take the definition called XF. This is the standard notation. So XF basically means that for each F, right, for F you can restrict to Fx. Right, so this is F of X is the Stokes, right? So F representative of F, right, in the Stokes. This guy, you take all the points. So you take all the points in the skin, such that this Fx is not in the maximum ideal of local ring. Okay. Mx. Okay, so in the O of X. Right, so notice, so this is skin, right? So this guy is a local ring, right? This guy is a local ring, so there's a unique maximum ideal called M of X. So I take all the points such that the representative of this F is not in maximum ideal, or simply speaking is that if you write a function, if you view F as function from OX x to all x quotient n of x, then the f is not in n of x. Basically, you can think that f is non-zero. Okay. So simply speaking, that we take the function which is SF. Okay. Okay, so let's working on the fine skin. Right. So a quick example is that I haven't say what is the lemma, but it's very quick. So example is that if you take x to be a fine, right? So let's say f is a fine, then what is xf? So xf basically is like all the now x is prime ideal, right? So you restricted f to be prime ideal. So you restricted f into so now the stocks, so this f, right? Just mapped from A to A localized at P. Okay. So this guy will just be f divided by 1. Okay. So f, you're just saying f divided by 1 is not belongs to maximum ideal, which is PAP. Okay. And so this means that f cannot be equals to, let's say, P, some element which is in P, and some element B which is B not in P. Okay. But this is essentially the same as F 9P. Okay, you can check out by yourself, right? Because if F in P, then B times F will be in P. Then this violates right? So B is not okay. So let's see. So F is not equals to B P divided by B, right? So means that yeah, let me just okay, so let me just write as this. Okay, so let's do the converse. Let's say f equals to a divided by b, and a belongs to p, but b do not belongs to p. This means that you can find a u which do not belongs to p, such that u bf minus a is 0. Okay, so this is the definition of ring localization. And right, so now ua belongs to p, right? Because a belongs to p, but b do not belongs to p, and u do not belongs to p, right? So if this equation is true, then it must prove that f belongs to p. Okay. So if f cannot be equals to a divided by b, b do not belongs to p, and a belongs to p, then it must have f do not belongs to p. So this is the proof. Okay, but f do not belongs to P is the distinguished open set containing represent f, right? So this is exactly D of f. Okay. So this lemma so this lemma, right? We just proved this lemma. So we're just saying that if you take it to the general scheme, right? And then if you define this as f, and then you take the affine, let's say B is the B is a affine open cover. Let's say you take, so U is affine. Okay, U is affine X. Then let's say F represent in called F bar, right, in B. Okay, so F bar is the projection or the restriction from X to U. Then U intersection, right? U intersection SF, right? So now this guy is a affine subset, as we proved previously, will be D of F bar. Okay. So this theorem is very simple. Okay, but let's tell you what. Let's tell you a very important thing is that XF, right? One can write XF in terms of since X has a affine open cover, right? So XF can represent X as intersection with all X, and the XF intersection with all union of affine, right? So B now B is affine. Then this is the same as F union of X intersection with all affine. Okay, and also XF. Okay, this is affine, and this is intersection. Okay, so you get the union of all affine, or so each SF union B will be D of F bar. Okay, so this tell me that this shows that SF is what is open. Okay, so this is the only thing that we need to know, right? So basically, we need to say we just need this set to be open. Okay, so now we go back to original proof, right? So we'll go back to original proof. Okay, so now very simple. So let's see, let's say a proof. So let's concede, let's say U be the open subset. We take any open subset, okay? And then we take Fg belongs to all of U, and let's say suppose Fg equals to 0. Okay, so this means that if you restrict on stocks, right, you get f of x times g of x is 0, right, for every x belongs to x. Okay, so I can consider following two set called y, right? Y is x belongs to U, and the f of x belongs to the maximum ideal of x as a previous defined, but the previous we defined is not equal to, now we define equal to, right? So it's in and previous we define is not belong to. In this way, we define belong to. Then we define z to be x belongs to U, and f of x, g of x, right, do not belongs to m of x. Belongs to m of x. Okay, so by the previous fact, right? So y and z are close because we proved that by our lemma, right? Because previously we say that the complement of y and complement of z is open, so y and z are close. And obviously that U, right, should be equal to Y union Z, right? Because every X either belongs to one of it, okay? So we have this. Okay, so now, so since what U is irreducible, because the subset of the irreducible space is irreducible, right? So this tell me that y and y equals to U or Z equals to U. Okay, so let's suppose y equals to U. Okay, if y equals to U, this tell you what? This tell you that f of x, right, belongs to m of x for all x belongs to U, right? Okay, but what this mean? What does this mean? Okay, what does this mean? So now you are saying that f of x belongs to m of x for all x belongs to U. Okay, so let me just go to another page. Okay, so where you're saying that f of x belongs to m of x for all x belongs to U, right? But remember, U is a subset of the open subset of skin, right? So I can consider the affine subset. So let's consider the affine. So now we use the technique I say, right? So we consider affine subset of U. Let's call this affine subset W. If I restrict f of x to m of x for x in W, then we get affine skin, right? Then we get a affine skin property. So we have f of x belongs to PAP. Okay. Then by our previous proof that f of x belongs to P. Okay. For all, sorry, it should be FP, right? F raised to P. Right. Now because now if I consider affine subset, these points become a prime ideal of the affine subset. So FP belongs to PAP, and FP belongs to P. Let's say this means that the W come from the spec A. Okay, so FP belongs to P, right? So but for all P, okay, for all P. So this tell you what? This tell you that F is so now F. Yeah, so it should not be FP, should be F divided by 1, right? If F dy divided by 1 belongs to PAP, then F will belong to P. So F belongs to every prime ideal. Okay, so that means F belongs to the intersection of all the prime ideal. And what is the intersection of prime ideal? It's the neo radicals, right? It's a neo set, or basically all nilpotent. Okay, but as we said, right, this ring is reduced, so this guy is empty. It's 0. Okay, so this tells you that F is 0. Okay, so now we prove that for every affine subset, F is 0. Then by the Goulin property, this U has an open affine cover. So if F is 0 in every affine open subset, then U is 0. Okay, so let me write down. So if it's 0 on every affine open subset of U. And we also know that U is a skin, right? Subskin. So U has a subskin. So subskin U has a fine open cover. So by gluing property or whatever, F is 0. Okay, by gluing property. So F is 0 on global sections. So on gamma X reduced to U. This basically is OX U. Okay, so this is our final proof. Yeah, finish. Okay, so this will prove that if f is equals 0, then one of it must be 0 on the integral on the whole space. Okay, so this is the Harson's proof, right? But Harson didn't give you this detail. Harson just very textbook, very short. So you need to understand by yourself. Okay, so hope you guys subscribe to my channel, and yeah, I'm gonna to talking about the module associated with a fine skin in the next video. But before we do this, I need some time to talk about some functorial property. I mean, algebraic geometry is very difficult. There's so many details. I try to do my best.